that, what would you say that compound was? Name that one for me. That's a C followed by an L, for those of you giving me a hard time for how I drew it. Okay. It's not chloride, it's chlorine. What do we have now? Chloride. The name changes slightly. Well, why does the name change? Well, what we drew changed. Okay, our chlorine started as a neutral compound versus now it being charged. It has that negative charge associated with it. So when we go through to name our anions, what we'll end up doing is changing the ending of the anion name to an IDE. D as in dog. Okay? The next big complicated thing is how do we specify the charge on the ions? How do we know what charge chloride is versus what charge our cation is? Okay, so this is an extra rule that comes in when we're looking at our ionic compounds. Okay, there's two ways that you know the charge. Number one, you're told to memorize certain ones. So memorize those ones. If you haven't memorized it, guess what you need to do? Tell me what the charge is. Okay? And we'll specify that charge in the name using Roman numerals. Okay? What if you memorize none of them? Odds are you'll start getting questions wrong, because if you're required to memorize them, you do not specify the charge. By using the Roman numerals on a species that you are required to know the charge on, you are admitting that you don't know the charge, and you are now proving that you don't know how to name. That was kind of fun. Don't know how to name, and thus don't deserve any of the points. Okay, so you do need to memorize those charges. Okay? The next bit of information is if we look at a formula, does our formula carry a charge? Okay, well, one of the things that we haven't talked about quite yet is where our electrons are specified in a formula. Okay, well, we've talked about where the protons are specified in a formula. Where are the protons specified? Where would I specify the protons for this element? It's the atomic number. Where's the atomic number written right now? It's not, so I need to specify it. What is the atomic number for Ra? 88. Where do I write that number? The bottom left. I now know the number of protons. It's 88. What other information could I specify in this notation? The atomic mass, upper left-hand corner. And we'll do 226. What does that information tell us? That's our number of protons and neutrons. So if we subtract those two, we can get the number of neutrons. Where does that formula mention anything about the number of electrons? It does. It's charge. Where's the charge specified? Because I don't see a charge there. Go ahead. It's neutral. It has zero charge. Where is that information specified? In the upper right-hand corner, there is nothing written, which means the charge on that atom is neutral. For it to be neutral, how many electrons must there be? 88 to balance out the positive protons. Okay? So in the upper right-hand corner of every single formula, every single compound, every single thing, you have the charge specified. What is the charge on a chloride ion? Negative 1. Okay? That gives us information about the electrons. Okay? So, ones that you need to memorize. Everything on this chart that came out of your textbook is something that you need to memorize. Unfortunately, your textbook, for some unknown reason to me, also decided to include a bunch of other things that you shouldn't memorize. Okay? The giant red line through them is why, or the ones you don't need to memorize. Why should we not memorize the charge for lead? There's multiple charges. That's too much work. So don't do it. Okay? You'll notice that for chromium, they've only specified 1. What do they specify? Chromium plus 3? I can't see through my own mark. Chromium plus 3. Anybody seen that movie, Erin Brockovich? Yeah. What was she freaking out about?
Water.
What in the water? Chromium ion. And chromium ion of what charge? +6. Why is +6 not written up there? I have no idea. They shouldn't be specifying it as only +3. It is not only +3. Okay? That is why I put the giant red slash through them. All the other ones you are responsible for that are shown up here. Are there patterns within this? Yes. And we'll talk about where those patterns come from hopefully later today. But you'll notice in your first column it's a +1. Second column it's a +2. Our third column, which seems a bit odd because I'm calling this next one over here, our third column is a +3. You'll notice that I then have this giant gap in between where I haven't specified charge for you. Oh well. Next column is -3. Interesting, the sign changed. We'll talk about why that sign changes in a second or later today. Next one, -2. Next one, -1. So worst case periodic table, brain hemorrhage as soon as you get the exam, write down those charges across the top of the columns, you now have them memorized. Ta-da! Okay? Make sense? Okay. Let's take a swing at naming practice. Let's name the compound below, NaCl. You already know the name to this, but follow our rules. What is the name for Na? Sodium. So we merely write sodium. Because it is the cation, we don't change its name. We leave it entirely alone. What is the next atom? Chlorine. Ooh. If we wrote sodium chlorine, we'd get marked wrong. Because chlorine is just Cl, not Cl minus. Okay? This is now chlorine that is interacting with sodium. We have a compound. I must change the anion name. So I'm going to grab the suffix of chlorine and I'm going to turn that into an IDE ending. Just so happens for the chlorine, it's a relatively straightforward one. And I make this chloride. Okay. When I write out the name, I must also include information about the charge. Okay. Well, what charge is chloride? -1. When is it anything else? At this point, it's never anything else. It's not true, but it's never anything else. Which means, don't specify it. Okay. Not only does it mean don't specify it, when we're looking at our chloride, that is our anion. We'll never specify the charge on the anion. We will only specify the charge on the cation. Okay, the positively charged one. Okay, well, what is the charge on sodium? +1. When is it anything else? Never. Which means you do not specify the charge because it is one that you are required to know. If you are required to know it, guess who else needs to know it? Me and every other chemist on the planet, which means you don't specify it. So there's our name. Look at that. That was the name you guys probably would have shouted out if I just asked you to tell me the name of that compound. You knew that. Good job. Fantastic. Pat yourself on the back. Or not. That's fine. Okay, thank you. So how about the next one? It's a little bit harder. Cu is copper. Because it is our cation, we will not change its name. We leave it alone. Br is bromine, but the only time it's bromine is when it's by itself. Is bromine by itself? No, it is in a compound with copper. So I must change the name to make sure it is now clear that it is in a compound. I remove the suffix and I change it to bromide. Okay, just as what we did with the last one. And we now have copper bromide. A couple interesting things pop up out of this. In our formula, you'll notice that it says CuBr subscript 2. Why is the 2 there? I need 2 bromides to balance out the copper. Okay. Why do I need 2 bromides? What would the charge be on the copper? It has to be positive 2 because bromide is -1. If there's 2 -1s, what does the copper have to be? Positive 2 to neutralize it. And when we look in the upper right-hand corner, what's the charge? Neutral, 0. It must equal 0. Okay. So we know some information. Just by looking at that formula, we know that the copper is a +2. Move to the name. Where in the name does it say the copper is a +2 charge? Where in the name did sodium chloride specify the charge on sodium? No. Sodium was one of those elements that you were told to memorize, which means just by writing sodium, we know its charge is +1. Do you know the charge on copper? No. This name does not specify the charge on copper. And since you don't know it from your memorization, you must specify the charge. What is the charge on copper? According to our formula, it is +2. I now need to include that information as a Roman numeral right after my copper. Why don't we write 2 in, say, a different language, some alien language where they don't use 2s as symbols for our numbers? Okay? It's a standard format. We decided Roman numerals, that's what we stuck with. Okay? Questions? Okay. What if we went the other way? Well, symbol for magnesium, Mg. Symbol for oxide? Symbol for oxide is O. Bringing in the 2 specifies the amount of oxygen I would need to balance out the magnesium. Okay. Well, what is the charge on magnesium? How do you know it's a +2? I don't see the Roman numeral. You are required to have it memorized. Magnesium is a +2. What is the charge on oxygen? -2. Is our formula balanced? Yes. What does that mean? You better not put in that subscript 2 because you now unbalanced your formula. Okay. Iron 3 sulfide. Fe. Sulfur is S. What's the charge on sulfur? -2. What's the charge on the iron? How do you know it's +3? The Roman numeral right after it. It tells you what it is. Would our formula be balanced?
No.
No. If I just had one of each of those, I add it up, and what's my overall charge? +1. When we're making our compounds, our overall charge must be 0. So I now have to change the amount of iron and the amount of sulfur so that those charges balance out. Okay? Really what we're saying is that I don't know how many sulfurs I have. I don't know how many, irons I have. I don't know how many sulfurs I have. But when I add that up, it had better equal 0.
Right.
What are x and y? One equation, 2 unknowns. Those of you that have gone through algebra, what does that mean? You can't directly solve for it, so you guess. Let's say x is equal to 1. What would y equal? I would say y equals 3/2. Can I have half of a sulfur atom? No. So what does that mean? X was not 1. What should you do now? Try 2. Okay? See what happens. When you try 2, you will notice that y will come out to be 3. Okay? And now we have our formula. Your textbook does this, in my opinion, moronic crossover method. If you're happy with the crossover method, go ahead and do that. The last check that you should do, have you used the smallest whole numbers possible? Okay. Can I reduce the 2 any smaller by that same value to the 3? No. Why has this become important? Because there's another possible solve. 4 and 6 solves that exact same equation. But can I reduce the 4 and 6 to smaller values? Yes. The crossover method will almost always give you a higher value. Okay? Make sure you reduce it down. Yes?
I was wondering how,
Yep.
how high do you think you have to go?
In general, for what you guys are doing for your guesses, you're going to go up to 3, potentially. And I don't think you ever go beyond that. All right? Other questions? So these are your ionic compounds. We took a metal and a nonmetal. Officially, we took one type of nonmetal and one type of metal to put them together. So we have a binary ionic compound. Okay? So what we've gone through and done is evaluated to get to your formulas. That's what we did for the copper bromide. That's what we did for the iron sulfide. That's what we could do for the aluminum oxide. Okay? All of those end up going through the same idea. You use that formula, you predict it out. Okay? Using basic algebra to solve. There are cases where we have something known as polyatomic ions. So we can take nonmetals and we can bind those nonmetals to each other in a covalent compound to generate a new ion. Here's a list of them. This is not an extensive list. There's a heck of a lot more than this for your possible ions. Okay? That's a lot to now add on top of this, because you are now responsible for the symbol and the name. Well, what is the symbol for the acetate ion? C2H3O2 minus. You're responsible for that complex symbol, just like you're responsible for knowing what zinc is. What is zinc? Zn. You now have new elements, if you will, to memorize. What makes these more difficult is you start seeing more numbers incorporate into these, multiple letters. You must treat them as their own unit. Okay? So when I look at the chlorite ion, it's ClO2. Why is the 2 there?
Takes 2 oxygen.
The 2 is there because that's what makes this the chlorite ion. I cannot change that 2. Just like sodium. What is the symbol for sodium? Na. Why is the A there? What happens when I get rid of the A?
You get nitrogen.
It becomes nitrogen. A is as much a part of the name or the symbol for sodium as this 2 is part of the formula for chlorite. I did pick chlorite. Okay. You have to keep it linked. This does become trickier because you see 2s show up in other cases. Right? For instance, why is the 2 in copper bromide? That 2 is to have the bromide balance the copper. That 2's meaning is a balancing of the formula. The 2 meaning in chlorite is what makes it chlorite. Same symbol, entirely different meanings. You have to recognize that difference. This takes practice. Okay? Lots of practice. But ultimately, all it is a rule. Do you know the rule? Good. You know how to name. You don't know the rule? Well, you can't name. So it's incredibly boring as a lecture, which is why it's all recorded and posted online. Okay? A lot of complex ions to go through and memorize. Okay? I went through and said, you know what? I don't think all of those are important to memorize. I think only some of them are important to memorize. I flagged those with the purple stars. The purple stars you absolutely must have memorized. What about the other ones?
It's helpful.
It'll be helpful. It'll make it easier to go through and name, because when you get to the homework, can I ask a question on the homework about the nitrite ion? Yeah. Okay. Do I expect you to have it memorized on the homework? No. What do I expect you to do on the homework? Pull up the table that has what nitride is. Look at it. Look it up. Use the tables. By doing a bunch of practice, you will start to memorize these naturally on your own. So I would recommend practice over note cards. Note cards will help, but the practice is what's going to really beat that into your head and get it stuck in there. Okay. The, what is it, library, tutoring center, does a teaching lesson on nomenclature. Watch the nomenclature video, go to the tutoring center, have them work through problems. They come up with some weird mnemonic devices to help you memorize, which I never remember. There's something about camels eating dinner at midnight, something like that, which helps you memorize some of those elements and particularly their charges. Okay? It is helpful, okay, as a last-ditch mnemonic device to help you memorize those particular charges. Okay? So I would recommend that. I'll try and post that information more specifically about when it is. It's on Fridays, and sometimes they do it in the middle of the week too, but for the most part I know Fridays. Yes?
The whole 8-night rule, does that pertain to, is it relative only to the other charges?
8-night,
Yeah.
purely memorization.
Yeah.
There's a bunch of, again, in my opinion, stupid mnemonic devices. Well, 8 means you have more oxygens. Okay? Well, sulfate has more oxygens than sulfite. But chlorite has less oxygens than chromate. But you notice your chlorite and perchlorate. Both of those are 8s, but they have 4, 3, 2, 1 oxygens. When we look at the sulfates, you have sulfate and you have sulfite. Okay? Well, which has more oxygens? Sure, the sulfate. What's more? 4? 4 is more than 3, but isn't 2 more than 1?
Yeah.
Isn't 3 more than 1?
So it's only relative to its counterpart.
Yeah. Which means you have to know the counterpart. So if you memorize 1, you know the other based on this, oh, it's 8 versus 8. If you memorize 1, you know the other because you memorized it. There's no need to do the stupid 8-8 thing. Okay? It's completely silly. Okay? Kind of makes sense? And yeah, it gets mentioned. But it's strictly dumb. Okay? Questions?
What's the purpose of memorizing all of that?
What's the formula for each of these compounds? There's your purpose. Okay. Why do we want to know the formula? Do you really want to write out the name of every single compound? We've been talking about Cu, Zn, O, F. Do we really want to be saying copper, zinc, oxygen, fluorine every single time? No. We want some modified, simplified version. That's why we need the symbols. Okay? That's why you have to be able to interconvert back and forth between them. Okay? I'll give you 5 minutes, actually 2.5 minutes. Pick any one you want, go through and work with it. Then I'll switch to the names to formulas, I think. I'll pick one example out of each, and then we're going to move forward in the next 5 minutes. And if you got questions. So our first question is to evaluate magnesium sulfate. Symbol for magnesium is Mg. The symbol for sulfate is SO4. Not sulfide with a D. The D means the element. T means complex ion, your polyatomic ions. There are 2 exceptions to that. Hydroxide with a D, which references
Oxygen.
hydroxide is not just oxygen, that would be oxide. It's hydroxide. It's OH minus.
Oh,
Okay. The other exception is cyanide with a D. That is Cn minus. Okay. So if you see a D showing up in your ending, it's a single atom. Okay, or a single element, I should say, not a single atom, a single element. If you see a T, it's a complex ion, with those 2 exceptions, the hydroxide and the sulfide. So when we look at this and we see that T in there, we immediately know complex ion, it can't just be sulfur. Okay. So now we'd have to say, okay, did I memorize what sulfate was? probably haven't memorized it yet, fair enough. Okay. You need to. It's SO4. Okay. The next part of this is making sure that you have the proper number of the magnesiums and the sulfates. How many of each of those are present? Well, to figure out how many of them, you need to know their charge. The magnesium is what charge? +2. How do you know that?
In your chart.
2 ways. You can use the periodic table and you've memorized what those columns mean. Okay? Or you just memorize the charge on magnesium. Either way, you did some memorization. Charge on the sulfate? -2. The reason you know that? Straight memorization. There is no cheat, if you will, on that one. If I had one of each, what would my charge be? 0. I'm at my formula. It's MgSO4. Okay? So, formula to name. Here are those 3 names. Which one do you want to look at? Ammonium sulfate is the one we'll pick. So, what we'll do is we convert our formula into the name. The formula for our NH4 correlates to what name? Ammonium. How do you know that? It's one of those ones you would have to use the table for, because I didn't actually tell you to memorize that one. Okay. So you would just look it up and see what that formula corresponds to.
It's also in lab.
Doesn't matter, you still had to look it up. SO4 is sulfate. Okay. So there's the name straight down. Okay. Are you required to know the charge on sulfate? Yes. Are you required to know the charge on ammonium?
Probably.
Yes. You need to know the charge on all of your complex ions, which means you look it up, it'll tell you the charge. Okay? So if you know the charges, guess what? You're done. It's ammonium sulfate. There's nothing else to write. That is the name. The question you may encounter is then why did we include this 2? To balance our formula. Ammonium is a +1 charge, sulfate is a -2. By writing the name ammonium sulfate, I know those charges already. When I now convert it to the formula, I know I need 2 ammoniums to balance out the charge. I don't specify the charge because the charge is already given to me. The 2 only shows up in the formula, not in the name. Okay? Practice, practice, practice.
Okay.
If you've gone through the textbook and you're like, oh, I think I got it, I don't need any more practice, open up your lab manual. Your lab manual is 5 pages of nomenclature. And it's not a gentle 5 pages of nomenclature. It's a lot. Okay? Trying to really beat it into your head and pick up these rules. Once you've got the rules down, it's simple. You just name. By the end of the semester, I would bet that almost all of you are like, just give me a test on nomenclature. Okay? That would be so much easier than having to be tested on everything else. Okay? So,
Nomenclature's going to be next week's lab?
it's not next week. It's the week of the 6th and the 8th, so it's 2 weeks. Holy crap, is it really next week?
Yeah.
Whoa, okay, your nomenclature lab is next week. Holy crap. I got a lot of work to do. So, let's move forward. Ooh, geez. The reason I repeated this slide is this gives us our big summary of our subatomic particles that you need to know. An electron is what charge? Negative. A proton is what charge? Neutron is what charge? What's the mass of an electron? 0. Good call. Mass of a neutron? Mass of a proton? 1. You need to know that information. That's why that's there. Sounds like you all got it. Within our atomic notation, better referenced as nuclear notation, you take the symbol of your element. Your mass number is specified in the upper left-hand corner. Lower left-hand corner is the atomic number. The atomic number tells you the number of protons directly. The mass number tells you the number of neutrons indirectly, because it tells you are protons and neutrons. So you have to do a calculation to determine the number of neutrons. We just talked about today one other addition that we can make to this. What is written in the upper right-hand corner? The charge. That charge is the balance of our protons and electrons, including their charge. So it's the number of protons times the charge on a proton, which you already proved to me you knew, which was 1, plus the number of electrons times their charge, which is -1. If our compound is neutral, that overall charge is 0, because the number of protons, the number of electrons equal each other. If it is not 0, then we must specify it. And we specify that by just writing a random, not random, but a correct number in that upper right-hand corner. So if I wanted to say that this element had a -2 charge, what I would write in the upper left-hand corner is -2. Okay? Your textbook likes to reference it as 2 negative. They're both equivalent. I like emphasizing the fact that there's a negative in front. So you'll see me do the charge and then the magnitude. Okay? You'll also always see me write +1, okay? Or at least just a positive. So the charge is more important than the magnitude. Specify the charge, then the magnitude. My general opinion. Either way is valid. Questions? Simple and weighted averages. We're going to work through this one time, the really fast way that we talked about yesterday, and then we'll zero in on just our formula. If we were going to take our weighted average for, say, hydrogen. So, oops, I got rid of that slide. So we have 2 isotopes of hydrogen commonly. We have protium and we have deuterium. If we were going to determine what number should be reported on our periodic table, it's the average of all of the isotopes. Right? So what we might say is, well, I'll take the mass of the first particle plus the mass of the second particle and divide it by the number of particles, which in this case is 2. Right? The result here gets me what number? 3/2. And I keep forgetting what I'm trying to write. 3/2, which equals 1.5. If we take a look at the periodic table, is that true? No. Okay. So let's take this formula, our real quick just average calculation, and break it down into what it actually means. I wrote it really big. What we are saying is this is 1/2 plus 2/2. Okay. Which is also the same as saying it is 1/2 times 1 plus 1/2 times 2. 1/2 as a percent is 50%, or 0.5 times 1 plus 0.5 times 2. By taking a standard average, we are assuming an equal weight to each of our values. Okay? What we just did was break that all the way down so that we can very clearly see that. So let's rewrite that. So I'm going to erase all this. What we are doing is taking our percent of A times our mass, or whatever it is, in this case it's our mass of A, plus our percent of B times the mass of B. This equals our now weighted average. Okay, what does this mean? Well, it turns out that hydrogen is not 50% of each. It's more like 99% of the protium and 1% of the deuterium. So we can now interpret our information in. We'd have 0.99 for our percent of A times, what's the mass of A in this case? Thank you. Plus our 0.01% of B times the mass of B, and then the mass of B is 2. We add this up, I see your hand, give me a sec, and we should get something that was roughly 1.01 when we punched into the calculator, which comes out darn close to what the periodic table tells you. Okay? Those numbers I just guessed and made up and put in there, and they just happen to work out. How would you know what those numbers are? You could look it up. On a test, it's going to be very difficult to look it up. So what do you do? Whoa, memorize. Damn. You guys think I'm awful. It's given to you. I'll tell you what those values are. Okay? Yes. So those percents are things that will be given to you. Okay? Or I can give you the weighted average. Believe it or not, you always have the weighted average. Why do you always have the weighted average? That's what the periodic table reports. So I can tell you the mass of two of the particles and just one of their percents. Actually, I can tell you the mass of one of them and one of its percents. Okay? You would then be able to tell me the mass of the other particle. Because you know the weighted average from your periodic table. You also know the percent of the other one. How would you know the percent of the other one if I only gave you one? Subtract it from 100. If there's only two particles, the total of them must equal 100. Okay? So, understand how a weighted average works, or there you go. Memorize that little equation, plug and chug. So round 2, plug and chug. You got questions, raise your hand. I'll come to you to try and help you out. So we take the formula that we used, plug and chug in your values. Some of the ones that are trickier to track down, your percent of B. How do we get the percent of B?
Subtract of this 60.
We know A plus B has to equal 100. I know A is that 0.6, whoops, 60.11 plus B equals 100. I can now solve for B. Remember, when we use our percents, we have to convert them into their decimal value. So we'll get the 39.89%, assuming I did that math right or heard somebody do that math right. Convert it into your decimal. The last one that's difficult to track down, 69.72 came from periodic table. Now you do the algebra and you solve for B. Okay? That is it. Okay? So it's as simple as just plug and chug in your values and you just move your way through. Okay? Real quick approximation here. What should B be? I know it sounded kind of weird. Bigger or smaller than 68.926?
Bigger.
Why should it be bigger? Because we're looking at the average. If our average result is larger than 68.926, the other value had better be larger than 68.926, because otherwise it can't average out. Okay? Not only should it be larger than our 68.926, it should be larger than 69.72. Because 69.72 is the average. It's the in-between point of our two extremes. Okay? You can push this further by looking at their percents and deciding how much larger we would expect it to be. I will leave that to you to figure out on your own, or come talk to me after class. At this point, you've got the basics to be able to go through and solve it mathematically with your numbers. The rest of it is an approximation skill. Questions? Yippee. Heavy water. So we brought up this concept of deuterium. Heavy water just means that instead of having hydrogen or protium in your water, you have deuterium. That's it. Okay. D2O, because we now have deuterium and it has a slightly different mass, changes how it reacts and interacts with other molecules. We can use or witness that change in very carefully designed experiments. Okay. D2O does exist in nature, just very small abundance. So some people will actually build in their backyard a purification method to isolate D2O. Why? Because we have tons of water. All you got to do is pull the D2O out, and now that it's pure, you can then sell that to somebody else. So it's allegedly a relatively simple process. You can purify D2O and sell it to somebody or to a research group for a significant amount of money using what was effectively a free resource to you. Right? So it can be kind of a neat process. Chapter 5. So now what we're going to do is skip the second half of chapter 4 where it looked at light and electrons, because that is a haymaker of a problem. Okay? So I will highly recommend that you review the second half of chapter 4, read that, be super familiar roughly with that concept before we start class on Thursday, because that will be a doozy of a lecture. It's a lot of material going through it, and it's very difficult to understand. Okay? In chapter 5, what we now do, since we've got the basic structure of our elements, is we go through and start saying, okay, well, how do we organize now this basic structure of our elements? So they go through a bunch of history, a bunch of science or scientists' names on how they decided to organize our periodic table. Our initial discovery organized them according to triads. Okay, well, if you only know the first 3 rows of our periodic table, you're going to see triads. You're going to see groupings of 3. Because you don't know all of the other elements. So that was one of our initial patterns. They just looked at it and said, well, these 3 elements all act very similarly, so I'm going to group them. Okay? That moved further on down the line into something known as the law of octaves. Okay? And they were grouped according to 7s. Okay? Somebody that knows music can explain that better than I can. I don't know music, so that doesn't work. Okay? But in 1865, they had a significantly larger amount of elements. They could start to notice larger patterns. Okay? Remember, both these time periods, 1800s, do we know of the existence of an electron yet?
No.
No. That happened in the early or late 1800s, like 1890s. We don't even know an electron exists. We don't know a proton exists. We don't know a neutron exists. All we're looking at is that I take this pure element, and when I mix it with oxygen, I get this product. If I take another pure element and I react it with oxygen, I get a very similar product. That's a bit odd. So I'm going to group them according to that categorization on how they reacted with another species. Okay. Where this really comes together is Mendeleev. So he's the big name you should remember on this. Mendeleev went through and organized the elements on our periodic table according to atomic mass. If we look at our periodic table now, is it organized according to atomic mass? No. It looks very, very close. As we go hydrogen to helium, lithium, beryllium, boron, carbon, let's make sure I don't miss the exception, nitrogen, oxygen, fluorine, neon, everything is increasing mass. Where are we? Sodium, magnesium, aluminum, where's the stupid exception? Is it really cobalt, nickel? Well, for lack of a better description, there's one. Cobalt, nickel. As we move from cobalt to nickel, what happens to the mass? It decreases. So if we had followed Mendeleev's periodic table, he would have exchanged those 2 elements in his table. Okay? So there's a reason we have the periodic table we do, because atomic mass does not properly group our elements. But all the way up to element, what is we looking at, 27, the grouping is pretty spot on. Okay? So that's how Mendeleev went through and organized his. He went through according to atomic mass. One of the biggest deals that came out of Mendeleev's table is that he noticed that there were sections that were missing elements. And he said, hey, I bet you there's an element in that spot that has these properties. We just haven't found it yet. That is why this table is really, really important. Because what ended up happening? He was right. He was able to actually predict the properties of a completely unknown element just based off of the organization of his periodic table. He found patterns, noticed those patterns, and predicted where things should show up. If he didn't know what they were called, he referenced them as the eka. Anybody know Greek? Latin? German? I actually don't know what language eka is, but I'm seeing if anybody knows. Does anybody know what eka means? It means similar to. Since you don't know, it's close enough. Okay. Eka means similar to. It's similar to the rest of the elements in that. So he referred to this one as eka aluminum, because it is similar to the closest element he had, aluminum. Right? That predictive power is really what calls this out. So if we go through and take a look, He predicted in 1869 the existence of something he referred to as eka-silicon. Color. Well, that's kind of boring. Almost all of our metals are gray. Whoop-de-doo. The atomic mass? We don't even know what a proton is, or an electron, yet he's predicting an atomic mass. That's pretty cool. What? Physical properties? He's predicting physical properties off of this? Melting point. Nice and descriptive. Good job. Okay. He's got all of these particular properties that he's predicting to be true. In 1886, we actually discovered what that element was. How close are his guesses?
Pretty damn good.
Pretty ridiculous. Okay. That is why we honor and recognize Mendeleev, because he was able to organize the periodic table, albeit wrong, but organize it in a way that allowed him to predict the existence of elements that we did not know existed. Okay. The pure definition of science. Okay. Incredibly impressive. Okay. One of the big things that came off our periodic table is it expanded to one additional group on our extreme right, and we refer to these as the inert noble gases. Okay. Really came about with the discovery of argon, 1894. Okay. Why these are important, okay, is because of our charge. Okay. In 1913, Moseley's defining a nuclear charge, and he said, okay, you know what, we can organize our periodic table better. Now that we know what protons, neutrons, and electrons are, we'll reorganize our periodic table according to the nuclear charge, which ultimately means the number of protons. The electrons are not found in the nucleus. Okay. When he went through and organized this, he noticed that still the same patterns that Mendeleev predicted still held true. Because under most conditions, it did work according to mass. Okay. Why would we expect mass to increase as the nucleus gets larger?
More protons.
There's more protons. And what are protons? Mass. So it does in general trend according the same. You run into some exceptions, likely due to the number of neutrons being added in each of those particular cases. Okay? The noble gases become incredibly important and end up forming our capstone on our periodic table. Okay? They're our capstone because what they have proved is now an inert system. What does that mean? They do not react with anything. Everything we've talked about is striving for neutrality. We don't want charge. So when we name a compound, we balance out the ions so that we don't have charge. Our noble gases are neutral, which means they are incredibly stable. Stable now because they don't have that charge. Okay? Why has this become important for us? Well, think back to all the charged elements. They are charged because they are doing whatever they can to look like a noble gas. What can we change about oxygen or fluorine to look like neon? What's that? So fluorine as an atom is neutral. 9 protons, 9 electrons, and 10 neutrons. How can I make fluorine look like neon? Why electrons? If I change the number of protons, it looks like neon. What happens when I change the number of protons? It becomes a different element. It's no longer fluorine. So I can't change the number of protons. Well, the neutrons aren't contributing to the stability. It's the electrons. So what does fluorine do to look like neon? Changes its clothes by putting on an extra electron. By gaining that extra electron, what happened to now the charge balance within it?
It's more negative.
It becomes more negative. How much did it become negative by?
1.
-1. What was the charge for everything in that fluorine column? -1. What does oxygen need to do to look like neon? It needs to gain 2 electrons, which means its charge would become -2. How about sulfur right underneath it? Same deal, gaining 2 electrons. How about nitrogen? What does nitrogen need to do to look like our noble gases? Gain 3 electrons. What was the charge on nitrogen? -3. Interesting. Our periodic table has that information about charges already built into it. Whether you decide to derive it by understanding that the noble gases don't react is up to you. So within our periodic law concept, what we've got is that our elements reoccur in a repeating pattern according to their configurations in their atomic numbers. Okay? So those atomic numbers will notice and kind of organize. So everything within the column underneath fluorine has similar chemistry. Everything under nitrogen has similar chemistry to nitrogen. Everything under nickel has similar chemistry to nickel. Is it perfect? No, and we can talk about that later. Everything underneath beryllium has similar chemistry. So by organizing according to our atomic number, we get these general patterns that come out of this. Okay? One of the concepts that we're now lacking is what's happening with our electron energy levels. So where are our electrons in this whole picture? That's our second half of chapter 4. And we'll use that to understand some other patterns that we find within the periodic table. But before we open up that can of worms, let's find out what some of those patterns are first. Yeah?
Does that hold true for the sign?
What's that? Does the pattern hold in the bottom box as well? Yes, it does hold in the bottom box as well, but it's not, LA is not similar to TI. Okay. This bottom box is actually a subsection within. Really, this periodic table should be twice as long. Okay. So, groups and periods. Some new kind of phrasing that we can reference. Our vertical column, okay, we refer to as a column. Okay, at least that's how I refer to it. Sometimes you'll hear it referred to as a group or a family. So ultimately meaning the exact same thing. Okay? I never remember group, family, or period, so I always refer to them columns and rows. And even the columns and rows I confuse. Sometimes I refer to the column as the thing going horizontally. Okay? Whatever you want to say about that, feel free to say on your own time. The horizontal row is classified as a period or series. Okay? And each of those things carry different meanings. So when we go through and look at our individual groups on our periodic table, because they all act similarly, I can now group them and give them a name. So everything in that first column is known as the alkali metals. Everything in that second column is known as the alkaline earth metals. They just belong to that group. Okay? Just like we all have family names, and we can group ourselves according to our families, the same thing's happening here. Okay? So some of the more important names are shown up here. Your alkali metals, your alkaline earth, the noble gases, big one, and then your halogens. Okay? So your halogens are that second to last row on the right. Those are the primary ones that you're responsible for. You should know those. That said, alkali metals and alkaline earths sound way too similar to me. I get them backwards all the time. Okay? And I recorded that. Good job. Some of the other ones that we can throw in there, and I just think these are kind of fun to mention. Anything underneath oxygen is referred to as a chalcogen, or a chalcogen family. Anything under nitrogen is known as your pnictogens. I just like listing those because I think they're fun to say. You guys want to test it? How do you say that one? Chalcogens. Yeah, it's kind of fun, isn't it? How about the other one? Yeah, it is kind of fun, isn't it? You aren't responsible for knowing the names of those families, okay? But if you go outside of this class, you can then make fun of the other students. You're like, oh, you don't know the family name for the nitrogens? Those are the pnictogens. Why did you not know that? You must be an idiot. Right? Make them feel really bad for not being in this class. All right? Periodic trends and physical properties. What can we predict about francium? So what I've given here is a list of the elements. I didn't cover up francium, I covered up potassium. So let's predict some information about potassium. What can you tell me about potassium? What would we predict for the atomic radius, the density, the melting point, and the atomic mass? You're going to bust out a little Mendeleev skill and see what you can do. Okay, we heard some numbers. It's fine, we can go ahead and shout them out. 0.2. Why'd you say 0.2? It's in between the two values of sodium and rubidium. Where is potassium on our periodic table? Below sodium and above rubidium. So we would expect that trend to kind of follow through. How about for our density? What happens in our trend for our density as we move down our column? It increases. So what would be a reasonable guess for the density of potassium? 1.2. Reasonable guess for the melting point. What happened to the melting point as you move down the periodic table? It gets smaller, so it's a reasonable guess. 60, I'll accept that. Atomic mass? You just tell me what it actually was? So I heard a 40, so we'll drop in with the 40. Okay, those are our reasonable guesses. What do we get? 0.2, 0.227. Good job. Ooh, 0.86 for the density. Son of a... Okay. It's a guess, remember? Following a trend. That does not mean the trend is always perfect. Melting point, didn't we guess 60? That's pretty spot on. And our atomic mass, we said 40. 39. Good job. Okay. You'll notice that our density is way outside of the realm of what's happening on this. Can I still ask this question on the exam? Yeah. Okay. So what would be reasonable densities for me to include as a multiple choice test? Okay. So remember, what I would be giving to you on an exam question would likely just be this, the densities and these elements. What do you think would be reasonable things to put on there? What did you guys guess? 1.2. So that's probably a good thing to put in there as a possible answer, right? Yeah? Okay. What else could I put in there? 0.86. Okay. So we've got a bunch of possible answers here, and we've even got a D, impossible to tell. Which of these answers is correct?
No. 1.23.
Why are you saying none of them? Because you know the answer. Could it possibly be 0.72? Does it make sense for the density to go down? It does not make sense for the density to go down. It does not match the standard trend of all the other ones. So 0.72 does not make sense. 1.23 goes up. It should go up. 1.7, it went up higher than the other one. 1.7 doesn't make sense. The best guess is 1.23. Don't fall into the trap of telling me the answer because you know the answer. Science is about using the information you have to predict what's happening. Right? That does not mean it needs to be correct. We are done.